minute to log in. And then, but I'm excited about the turnout so far. And I think our seminar room at Virginia Tech may be having trouble. So let me try to help them out with logging in. All right, sorry, I think I did just hear from our seminar room in Virginia Tech, and they're still having trouble getting in. So let's give them another minute to try the link I just sent them. But thank you to all of you who are in and going. I'll get started in just another minute. Okay, I do see Virginia Tech VTTI on our list now, so I will go ahead and get started because it is 2:01. I wanted to say hello. My name is Emily Parcaney, and we are all here today to learn about the implications of damage and deterioration on the performance and serviceability of girder bridges. So this is the 5th of 6 webinars that we have been sponsoring and presenting Virginia Tech and UVA research. Just hopefully you guys have gotten into the audio system. Hopefully when you logged in, it called you. If it didn't, there's also the VoIP option. You can also dial in the numbers right here. And I guess please put in the chat box if there's a problem. So we do want you to use the chat box up here on the upper left corner, and we want to promote interactivity. We are going to have some poll questions. There's a couple times where you're asked a poll question, or you can write in your own answer. So please feel free to use the chat box as we go here. So I just wanted to explain that this is a series of webinars sponsored by the Mid-Atlantic University Transportation Center, which is a consortium of 6 universities led by Penn State University, but University of Virginia, Virginia Tech, Morgan State, West Virginia University, and University of Maryland are part of this consortium. So, and then this particular project is a joint effort, by University of Virginia and Virginia Tech. VDOT has also helped us with this project to disseminate webinars of our projects at the 2 universities. So we've been aiming for the 2nd Thursday in the month at 2 p.m. So we're doing it this Thursday, and then Thursday the 11th we're going to have 2 more speakers. Here's our webinar and the people presenting. So Kwon Ho-an and Jin Hee-gu from Virginia Tech. So hopefully you guys have signed up for that and will enjoy that one. If you do want a PDH certificate, I think last month we sent out like 13 certificates. Please email Jennifer Butler using this address, jav8md@virginia.edu, and tell us that you want a certificate, and we'll try to send those out to you next week. You can also find today's presentation. Both of these links are a little bit long and obnoxious, but you can more easily find it at cts.virginia.edu/MAUTC, M-A-U-T-C, and then that'll get you to the list of webinars, and then you can link to the presentations here. So hopefully you'll be able to find them. So as we get started here, I want to sort of ask who we are and who's in the room with us. So we're going to put our first poll up right now. If you guys can fill it in, we'll put it up for a minute or so. And then, I do want to get to our presentation, so this will only be a couple minutes. So I'm happy almost half of us are from state government. That's kind of exciting. And then we also have, a significant number of local government people and a relatively smaller number of university researchers. So, and part of that may be that we have multiple people in the room, which we're going to be asking in a minute. But This is actually very encouraging that we have our consultants, 40% state government, 10% local, and 20% academic. So this is very exciting. So I'm going to go ahead and end that poll. Thank you for participating there. Just as another sort of intro question, I'm kind of curious how many people are viewing with you. Whether you're in yourself with your office or with other people, just to sort of give us a feel for how many people are here. So it looks like a lot of people are by them or in their own offices, and but there's a few groups watching, so I'm kind of excited about that. So we actually got at least 2 big groups with us, and okay. So let me go ahead and end this. So it looks like most of us, and just so one more poll. I am kind of curious on your familiarity with bridges compared to other topics, and sort of curious, what your primary background area is, so that we get a feel for who's in the room here. Yeah, we're not quite seeing all of it. All right, so we had to argue in our room which one to put down there. So it does look like most of us today are bridge engineers, so that's actually pretty helpful to know that people are speaking to the initiated, I guess I should say. So okay, so this is just, again, I'm really happy with the, it looks like most people have been clicking in on the polls. We do have a few more people than we received. And yeah, there's definitely, please ask questions on the left-hand corner. Please, respond to the polls. Either one thing, I show several slides with, some little bit complicated graphics. So if you look up here, I'm not sure if you'll be able to see it, these arrows in the top right corner of your screen, that's the way to get to full screen. So you can actually go ahead and press that to see your own full screen, escape to get out of that. Hopefully escape gets out of it. I'm not going back here. Do I have another icon? Oh, we got it. Sorry, so you do not escape to get out of it. You actually have to go hover in your top right corner and find the arrows again to go lower. So sorry that this box is a little bit slightly off, but hopefully that'll help you be able to see the full screen. Okay, so I think with that, I want to go ahead and introduce our 2 people presenting to us. We're going to have Professor Devin Harris. We're going to have Dr. Amir Gitazi. And this is their topic, and I won't scramble yet again. I'm excited that they're going to go ahead and present this to us today. So again, if you have any questions, please chat in the chat box. I've heard from one person who had trouble getting in. And so I think, yeah, we're going to... I need to email somebody to tell them. So we're, yeah.
Okay, Emily, thank you very much. This is Devin Harris, and again, we're going to talk today about the implications of damage and deterioration on the performance and serviceability of girder bridges. We've broken this presentation up into 2 different parts, and I'm going to present the first part, and Amir will present the second part. Before we get into this, I'm going to give a little brief background on basically both of the speakers, myself and Amir. Amir will talk about himself. I'm an assistant professor here at the University of Virginia. My areas of interest primarily lie in bridges, structural behavior of bridge systems, condition assessment, finite modeling, and high-performance materials.
Good afternoon, everyone. This is Amir Gitazi. I'm currently a postdoctoral research associate at the Department of Civil Environmental Engineering at the University of Virginia, and I'll be assisting Professor Harris on today's seminar.
Okay, so I guess a couple of things. One is that this presentation is part of a project that's ongoing, supported by the Mid-Atlantic University Transportation Center. So we've provided our email addresses, number one, here, and then we'll provide them again at the end in case you have some follow-up questions or you want to provide some additional information or feedback. We'd be happy to receive it. So with that, I'll get into kind of the intro part of this presentation. We're going to start out with some background, introduce the overall concept, some of the problem statement, and then talk a bit about computational modeling, and then move into the challenges. And then Amir will pick up with kind of the analytical side, to talk about the investigation approach, some of the model calibration methods, and proceed with a parametric study, or the details of a parametric study, and to conclude with some of the findings, and then wrap up with some of our future research that we're planning on doing. Okay, so I'm guessing based off of the polling, most people are familiar with bridges in general, but I'm going to give some basic background for those who are not. Basically, our national highway system is categorized as one of the greatest engineering achievements of the 20th century. This is actually according to the National Academy of Engineering. Serves as a core component of the economic health of the United States. Some of the features of this highway system: it provides a corridor for the transportation of goods and people. It provides a coast-to-coast and border-to-border passageway for the nation's military in times of national need. And it historically has included roads and bridges. Now, when we drill down a little deeper into the bridge side of things, the bridges serve as a critical component of most people's lives. People travel across bridges every day. Some don't really realize they're traveling across them. These bridges provide lifelines between communities. They also control the capacity of the system. So if there's a bottleneck or there's an accident or a detour on a bridge, you end up dealing with major detours that are not necessarily the same for traditional roadways. When we have failures in these bridges, we typically have global system failures, loss of lives, detours, and significant economic hardships. In recent years, there's been a number of tragic failures that have brought bridges and the challenges associated with safety of these bridges to the national forefront of public scrutiny. Things like the I-35W collapse in Minnesota in 2007, the I-5 Skagit River Bridge collapse in 2013 from an impact, and then the M Bridge in Missouri in 2013 are some of these examples where we see these collapses, and then they make their way into the news, and people start getting concerned. The interesting thing about failures of bridges is they're often attributed to unforeseen events or man-made hazards, things like vehicle or ship impacts, fire, flooding, earthquake, and one that's really not even listed here would be something like scour. But to follow up with that, the issue that we have in the transportation community is not really these one-off events. It's really condition states of these in-service structures. It really represents one of the greatest challenges that transportation agencies are dealing with. How do we maintain and preserve our existing infrastructure? So according to the National Bridge Inventory, the latest report, or at least the latest database dump from 2013, we have more than 600,000 bridges in the national inventory system, National Bridge Inventory. This doesn't necessarily include some of the bridges that are less than 20 feet that are not part of that inventory, so it's actually even larger than that. Of this NBI inventory, National Bridge Inventory, 10% of these are classified as structurally deficient, and 14% are classified as functionally obsolete. In reality, these functionally obsolete ones are really more of a serviceability. There's low guardrails, inappropriate approach bends, things like that fall into that category. When we deal with the structurally deficient, these are the ones that really hone in on safety of the structure. And with these structures, all these structures, maintenance is a growing challenge for both federal, state, and local governments. And it's really these routine structures. The routine structures, what I refer to, are things like highway overpasses, short to medium span structures. These structures suffer from various sources of in-service deterioration or degradation. And when we look at the infrastructure as a whole, transportation officials are behind in their ability to keep up with this maintenance. We're on this 2-year type cycle, and we're not ultimately able to repair everything at once. And in reality, it's not feasible to immediately repair anything anyway, both from an economic standpoint and a manpower standpoint. So the premise of structural health monitoring has come into play, and it's been around for, I would say, probably 10 to 15 years or so. And this concept or this framework, structural health monitoring, is intended to evaluate the system performance. So you may have heard this four-level approach. Level 1 being detection of damage, level 2 being localization, be able to find the location of the damage, 3 being estimation of the extent of the damage, and then 4 being the consequence of this damage. And basically this relates primarily to the structural safety and remaining life of the structure. And as we go from left to right, or level 1 to level 4, we see an increase in complexity in our ability to use this tool. And what this presentation really centers on is this level 4 part, really the consequence and the behavior of the system. As a result of structural health monitoring, there's been a number of new technologies that have been developed, and some of these are newer than others, but these technologies have been developed to monitor in situ behavior of these structures. Things like fiber optic sensors, wireless sensors, non-contact measurements. And what has sort of been a challenge is that there's been some reservations with integration of structural health monitoring into standard practice. Part of this has been because of skepticism by transportation agencies for this framework. There's been issues related to the cost and the application of these technologies relative to the inventory. And then one that's been presented very frequently is the potential for large amounts of data to come out of the structural health monitoring frameworks. And if you've heard the term DRIP, or data-rich information poor, this is kind of a common issue with structural health monitoring systems. The last one is our manpower and expertise required to interpret this data. So we're getting these large amounts of data. Ultimately, agencies do not want to have to employ a PhD in order to interpret the data sets. So we recognize that as a whole. So before we get a little bit further on, we wanted to ask one question. One is, what is your opinion on the concept of structural health monitoring for transportation applications? The answer is being tool that should be used more often. The other one is tool that has limited application in current environment. And 3 is undecided. You're undecided? All right, so it looks like we got a 50-30 or almost 50-30-11 split. We appreciate that feedback. Okay, so we'll keep going here, and I guess I'll say this as we speak. If you have questions that pop up, feel free to drop them in the chat. If we can answer them on the fly, we will do so. If not, we'll sort of reserve them for the end. So the challenge that we're sort of addressing with this project or this presentation here is that, as I said, transportation agencies are lacking, in my opinion and our opinion, is a fundamental understanding of the influence of these damage mechanisms on the system performance. The question that comes out of this is how field inspection data, which is what we commonly collect, can be used to correlate the impact of existing damage scenarios on the performance of highway bridges. So our goal in this project is ultimately to create a mechanism for integrating damage and deteriorating conditions into a measure of system performance. So we're trying to establish this framework. We're looking to make this framework applicable to routine superstructures rather than, say, some of the high-profile bridges, Chesapeake Bay Bridge Tunnel, Mackinac Bridge, Golden Gate Bridge, these high-profile structures that typically have constant ongoing maintenance. And another sub-goal would be to provide a linkage between design assumptions, maintenance, and behavior, which are typically uncoupled. In this study, we've limited it to steel girder bridges, which are one of the common types of structures that we see in service in the Commonwealth and pretty much throughout the United States. We believe that the approach is generic and should be able to be extrapolated to other types of structures fairly easily. And hopefully that'll come out as we move forward in this presentation. So the problem statement, when we're evaluating bridge system performance, we have a number of different approaches that we can take. One approach is and we'll call it the ideal approach, is that we can do full-scale destructive testing of in-service structures with damage present. We could also limit this to a laboratory study where we do scale bridge models. The challenge with these experimental approaches is that I would say they're not feasible, at least in the current day and age. They're not really feasible. The primary reason is the associated costs with testing these types of structures. When we take things down to the laboratory scale, there's issues associated with scaling and simulation of the actual boundary conditions, loading environment, something that's representative of an actual in-service structure. And that sort of points us to a different approach, where we're able to use things like computational modeling as an alternative. And what we're trying to do is ultimately satisfy the differential equation of the system using energy principles and satisfy equilibrium and compatibility of the system to solve the problem. So computational modeling, basically in a nutshell, we'll say is mathematical models of the structure. We have a number of different approaches, things like classical analytical tools, classical analytical models where we have closed form equations. These things tend to be more applicable to simple structural components, things like beams, columns, frames, and they may not be able to, or typically not able to, represent complex structural systems like a bridge where we have distribution behavior, composite action, complex interactions of the various components. In these other numerical models, we have an assemblage of discrete parts. It's kind of a different, this mathematical model, but a different form. Assemblage of discrete parts, and we have associated these models with approximate results. The complexity of the model is affected by the desirable level of accuracy. So if we develop really fine models, we'll tend to get better results. Some common numerical modeling approaches that are out there, and some of these are a little older than others, but things like the grillage method has been around, kind of a planar grid model, frame analysis type approach, where we discretize the structure into a series of beams and transverse beams. Finite strip method, which is somewhat similar to the finite element method, where we're looking at a line element, and then the finite element method, which is what we're actually using in this study. So before we continue, we're going to ask one more question here. How familiar are you with the finite element method? And answers being not familiar at all, familiar from school, but no experience with application. I use this tool on a regular or an occasional basis, and I use this tool regularly. That's good. That's pretty good distribution. I guess I'll go ahead and end this one. So the person, oops, okay. I guess the person who uses this regularly, we're probably going to try and hire you after this webinar. No, I'm kidding. We're going to move on. Okay, so with the finite element method, for those who are not as familiar, it's a powerful tool common in engineering practice. There's a number of different packages out there. We use more of the complicated ones, ANSYS, Abacus, which are typically research versions of the finite element solution. It allows us to model complex structural systems, include geometrical details, evaluate things like load structure interaction, and as it relates to this particular project, integrate existing damage. And the challenge with this approach is that certain challenges must be properly treated to yield accurate results, and that's a very important thing. It's kind of the mindset of if you put garbage in, you get garbage out, and so it's actually very important that you try to model the actual phenomena that exist. So some of the modeling assumption and simulation techniques that need to be considered, some have major impacts on the accuracy of results, including things like element selection, mesh generation, loading and boundary conditions are critical. For these bridge systems, we need to be careful and cognizant of modeling structural details, such as internal reinforcement of the concrete slab, composite action of the system, interaction between the deck and the girders. And then as we take these models into the full nonlinear range, which is kind of at the core of this project, it's essential to capture the failure characteristics and ultimate capacity of the system. So we need to pay attention specifically to the elastic and elastic and inelastic behavior of the materials, non-homogeneous and brittle nature of concrete, post-yielding and strain hardening of steel. And then we also need to consider failure criteria. How do we stop the models? What constitutes failure? And for concrete, this is typically cracking, crushing. For our steel sections, this is typically plastic deformations. As we start looking at bridge structures, the thing that takes bridge structures a little bit different from our classical frame type analysis is the system behavior. And this is actually a very important one because when we look at design, we tend to treat things or design things on the element level basis. And as a result of this system behavior, there's a great deal of inherent structural redundancy due to the complex interaction of the components. Typically, as I said, it's simplified in design, but it's also simplified in the rating, which is the evaluation side of the in-service structures. Things like girder distribution factors, load modifiers, and a true measure of our system performance requires ultimately a fundamental knowledge of the concept of redundancy in the system. The last piece of this modeling approach that for our particular project that's actually very important is the damage modeling. The complexity of these models increases with the presence of damage being integrated, and the degradation usually causes additional failure mechanism or premature failure mechanism. Some of the common deterioration mechanisms in highway bridges, you're probably familiar with this if you studied anything with bridges: girder corrosion, section loss, rebar corrosion, whether it's internal to the deck or a pre-stressed concrete beam. We'll see delaminations in the deck, which potentially lead to spalling of the deck surface either on the top or the bottom. We could have global damage occurrences such as settlement, frozen bearings, or impact, or even fire. A majority of these previous research on these topics have focused primarily on the element level behavior, and this study really focuses on the integration of the damage into the system level behavior of these structural systems. So as we move forward, we have one more question for you. The question is, what damage or deterioration mechanisms do you consider to be the most critical for in-service steel girder bridges? Potential topics or potential answers: corrosion of the deck reinforcement, spalling on the top side or underside of the deck, corrosion of the girders near midspan, corrosion of the girders near supports. Okay, thank you for those responses. I'm going to, let's see if we can close up this poll. We're going to pass it over to Amir, and he's going to take you through the numerical side of this study.
Hello everyone, this is Amir again. Thank you very much, Dr. Harris and Dr. Parkini. So in the next part of this presentation, we're going to talk about basically on the details of numerical modeling approach that we use to evaluate the behavior of these in-service structures under the effects of damage conditions. But before we go ahead and get to the details of these numerical models, I would like to highlight two main issues that Dr. Harris just mentioned in the first part of this presentation on the limitations of the testing and experimental facilities that we usually have with these type of structures, and also the budget associated with failure tests of these type of system in service. So with that in mind, we developed a numerical modeling approach, a framework, as you can see in this slide, which consists of 4 different phases. And following these phases actually help us in 2 main categories. The first one is that it helps us tremendously to make sure that the modeling approach that we use in this study is adequate and accurate enough for these type of structures. And other than that, help us to make sure that we address all the challenges that we mentioned in the first part of this presentation. For each of these phases, we have developed a series of numerical models based on the experimental data available in the literature, and we try to use those available experimental data to validate and calibrate our numerical modeling approach. So in the next couple of slides, I'm going to give you guys a summary of these numerical models that we have developed specifically for the first 3 phases, these are actually the basics of our numerical modeling framework. So in phase 1, our focus was to understand the behavior of intact breach components, individual components, and in the category of the composite steel girder bridges, the main load carrying elements are classified as steel girders or reinforced concrete decks. So our goal in this phase was to address the first 2 challenges, including the simulation assumptions and selection of appropriate material modeling in our numerical models. So we selected two case studies. The first one was an experimental study on a series of high-strength steel plate girders, which was performed back in 1995. And among all the specimens that they tested, we selected the one you can see the geometrical properties in this figure. Is actually the numerical model that we developed for this specific girder based on the information that they provided for us in their test report. All the material and geometric nonlinearities in this model we extracted from the test report according to their tested specimen. On the other side, for the next specimen, we selected an experimental study performed by McNeese back in 1999 on a corner-supported 2-way reinforced concrete slab. And this is actually the basis of more of the numerical analysis of the reinforced concrete structures on the deck applications. In order to take advantage of the symmetry in loading and geometry of the structure, we simulated only 1/4 of the slab in our study. And again, similar to the case of the steel plate girder, all the geometrical properties and material characteristics, we extracted them from the test reports. For both of these models, we included all sources of material nonlinearity, including the nonlinear stress-strain relationship, cracking, crushing for the concrete, plasticity and strain hardening, and also appropriate failure functions for both of these materials. For the case of the steel plate girder, we also included geometric nonlinearity to capture the local instability and the nature of these T-ball structures by introducing the initial imperfection in the format of out-of-plane deflection of the wet plate and also twisting of the top flange. We performed nonlinear static analysis using the ANSYS software and Newton-Raphson as our nonlinear solver. For both of these models, from the analysis, we extracted the data or result at the specific location of the specimen and tried to compare these results with those available from the experiment. So as an example, if you take a look at these graphs on the bottom of the slide, you can see the comparison that we made for first the steel girder. That was the load versus deflection and midspan of the structure. We derived from the numerical analysis and we compared that to the experimental data. So as you can see, the model was able to predict elastic behavior and the ultimate capacity of the structure. Other than that, the model was able to capture the failure mode of the system, which in this case was governed by the lateral buckling of the web plate under the location of application of the load. On the other case, the reinforced concrete slab, our model was able to predict the elastic behavior up to almost 5 kilonewton of the applied loads, which is the first cracking point or first cracking load of this structure. And after that, we had the reduction in the stiffness, but there is a little bit of discrepancy between the numerical and experimental results, and that is mainly related to the fact that there are limited information on the test setup, on the test report, and also the boundary condition that we used during the test. So we made lots of assumptions in our numerical model. Other than that, as you can see in this figure, they had a limitation on the amount of load that they put on this structure in their test setup. But in the numerical model, our model was able to capture the full nonlinear behavior of the system up to the failure of this specific slab, which was caused by a combination of material yielding in the reinforcement, cracking in the concrete deck, and crushing on the top surface of the deck. In phase 2, our focus was to study the behavior of intact breeze superstructure. So as we validated these numerical models within phase 1, now we can combine them together and create a model of the breeze superstructure. And the goal is to understand, as I mentioned, the system-level behavior, interaction between these components, and finally the failure characteristic of these type of structures. So for this phase, we selected 2 experimental investigations. The first one was based on an experimental study performed at the University of Nebraska back in 1995, where they modeled and constructed a model bridge, single-span, simply supported, full scale in the laboratory. And what you can see in the picture is the numerical model that we have created for this specific structure based on the data that they provided us in their report. The second case was a 4-span continuous breeze superstructure, which was in service back in 1970s and was tested to failure by a research group from University of Tennessee. And again, you can see the numerical model that we have created for this structure. Both of these structures, they were loaded by a series of concentrated loads in the experimental program to mimic the situation of two side-by-side H2HS20 trucks. But before we go ahead and continue on the details of the modeling and the result that we got from this phase, I would like to ask you guys this question. Are you familiar with other ultimate capacity and failure bridge tests that have been published? Because as I recall from this phase of the investigation, we had a problem finding adequate test data and test results for the ultimate capacity investigation of these structures to validate our models, and within working. And the problem is that within this limited pool of data, only a few of those have been already published, and we had access to a couple of those. So if you guys can provide us additional information on this by filling in the text area and the chat area on the left side of your screen, or email us, that would be great. So let's get back to our numerical modeling in this phase. So all the assumptions regarding the material modeling and geometrical modeling of the different components in this bridge model were pretty much the same as we validated in phase one. The only component that we added in this phase was actually the way that we connect these components together, the action between the girders and the reinforced concrete slab. So with no evidence of loss of composite action in the actual test and experimental program, we assume to have full composite action by making the rigid connections between the top flange of the girders and bottom surface of the reinforced concrete. Again, we perform the same type of analysis, nonlinear static analysis, and we monitor the load versus deflection at mid-span of the loaded span of these structures. As you can see in these figures, the models, the comparison between the numerical results and the experimental data. For the case of single-span bridge superstructure on the left side, you can see the model was able to capture the elastic behavior, and we had some discrepancy between the results at the initiation of nonlinearity in the steel girders. And that can be attributed to the fact that these girders in this specific test specimen were built-up girders, and there were a significant amount of residual stresses which we were not able to include into our models because of the limited data they provided us on the amount of these residual stresses or on the welding procedure that they used to make up these girders. Other than that, on the second case, on the 4-span continuous bridge superstructure, where we had a roll-up load-shaped plate girders or girders, we didn't have this problem, so we had a good correlation between the elastic behavior and nonlinear region of the response of this specific structure. Other than these detailed information on the nonlinear behavior of the system, our model was able to capture the failure characteristic of these structures, which was actually the punching shear for the case of single-span bridge superstructure and a combination of plastic hinging and steel girders and crushing in the reinforced concrete slab for the 4-span bridge superstructures. The next part of this phase, for the first time, we classified the stages to failure for these specific structures, which started with stage A, cracking in the reinforced concrete slab, following by B, formation of the first yielding point in the girders, and then going through the stage C, formation of full plastic hinges, and ultimately the ultimate capacity of the system, which was classified as a stage D. I should mention that all of these stages, the sequence and occurrence of them, they are attributed specific to these structures, and for other structures, for other type of loading, other geometrical characteristics, they might be different in terms of sequence and occurrence. So we also perform a sensitivity study on one of these structures to see how the variation in geometrical and material properties will affect the occurrence of these classified stages to failure. Other than that, we defined the element level nominal design capacity for these specific structures based on the actual RFC specification, and we plotted those values as the green lines in these graphs. So if you compare the ultimate capacity of these three superstructures that we achieved from the numerical analysis, or also the corresponding values from the experimental program, you can see in both of these structures we have the significant level of additional reserve capacity over the design level. So that actually confirms that the complex interaction between the components and the redundancy that we have in these systems. And the concept of redundancy is overly simplified in nowadays design practices, mainly in the format of distribution factors between the girders and also the load modifiers. So in order to expand our investigation here, we branch out, and we had a side investigation on the evolution of lateral load distribution behavior on a couple of representative structures in service in the state of Michigan to see how these, the distribution mechanism in the system will be changed as the structure approaches the ultimate capacity. The result of these last two branch out investigation were published as a couple journal papers in the ASC Journal of Bridge Engineering. So with these first two phases, we addressed the first three challenges: the simulation assumptions, the modeling of the material, and understand the system level behavior. The last challenge that we had in this study was how to create a suitable model, an applicable model for including the effect of damage into the behavior of these structures. And in phase 3, we actually selected two types of damages which are believed to be the most common type of deterioration in these specific type of bridges, the composite steel girder bridges, which are the girder corrosion and deck delamination. So girder corrosion are usually happening at the either end of the structure as a result of leaking from the expansion joint or spraying from the passing vehicle underneath the structure. The corresponding damage mechanism would be a reduction in the thickness of the web plate, bottom flange stiffeners, and this type of damage scenario may cause the structure to reduce its ultimate capacity because of the existence of local failure mechanisms such as local buckling or web crippling or crushing of the end stiffener at the vicinity of the support. In the other case, deck delamination or any other sources of deterioration associated with the reinforced concrete slabs, we may have delamination as a result of freezing tying cycles or corrosion-induced delamination. In the case of corrosion-induced delamination, we have these horizontal three-dimensional planar cracking that is parallel and close to the ulterior surface of the reinforced concrete deck. And as opposed to girder corrosion, this may not cause the structure to fail or reduce the capacity, but we may have some impacts on the serviceability because of this type of damage as a result of premature local crushing failures of the top surface of the concrete deck. So with the limitation that we had on the experimental result on full-scale test of bridge superstructures with actually detected level of damage, we decided to select an alternative and validate these modeling strategy for damage scenarios within the element level. In order to do that, we again selected two case studies. The first one was a series of experimental investigations on the deteriorated steel subsections performed at Michigan Tech back in 2005, where they had these W sections and they reduced the thickness of the bottom portion of the web and portion of the bottom flange to simulate the effect of corrosion. And again, they had a bunch of models, and between those we have selected the one that you can see in this figure. We created the numerical modeling answers based on the geometric and material properties they provided for us in the test report. And the other case, we're interested to see how the delamination will be affected. Will be causing the structure to fail or reduce the functionality of the structure. So we selected the experimental investigation performed at the University of California, San Diego on the overlaid reinforced concrete slabs, and they had different slabs with different boundary condition between these two layers and try to understand how this boundary condition may affect the behavior of these slabs. So among all the specimens that they had, we selected the one that they used bond breaking agent as the lubricant material to simulate the ideal case of delamination. Again, similar to the case that we had in phase 1, in order to take advantage of the symmetry in geometry and loading, we only modeled the 1/4 of these specific slab. In order to simulate the contact area or the interface area between these two layers, we use contact elements from the ANSYS that are able to transfer the compressive stresses between these two layers, and they are free against the tensile stresses. For each of these cases, we actually developed two numerical models, one with the intact configuration, the other one with damaged configuration. We performed the same type of numerical analysis on those and try to validate them by comparing the result that we got from these numerical investigation to the experimental data. In the case of corroded steel girder, as you can see in the left figure, our model was able to predict the behavior of the system in the elastic region and also the ultimate capacity and softening stage. And other than that, the model was able to capture the failure mode of the system, which was governed by global local buckling failure, buckling of the web plate at the middle height of the web. And other than that, if you compare the results that we got from the intact model and damaged model, you can see the level of reduction in the capacity that had in this specific specimen because of the existence of this type of damage. On the other case, the overlay reinforced concrete slab, we had these two models with the intact configuration where we had the full bond between these two layers of concrete, and also the delaminated case where we used the contact elements to make the separation between these two layers. And as you can see, the numerical models were in a good agreement with the experimental data, and again, comparing the results from the intact model and damaged model, you can see the amount of reduction in the capacity as a result of existed damage configuration. So with all of these phases, first three phases, we actually established a comprehensive foundation of our numerical modeling approach, and we address all the challenges we mentioned in the first part of this presentation. So the last part would be to evaluate the system behavior with integrated damage. So objective of this phase, or last phase of this project, which is the key role of this investigation, is to integrate the damage mechanism into system level models and characterize the impact of damage on system capacity, system ductility, and redundancy, and also the safety of this type of bridge superstructures. So in this phase, we actually started our investigation with a little sensitivity analysis, and we updated one of the bridge models that we have validated in phase 2. This was the bridge that was tested at the University of Nebraska. That was a lab test bridge, and we tried to include some representative case of damage into the model, like delamination, corrosion in the girders, lateral impact, lateral deformation as a result of vehicular impact, and also the fire attack. And the values of the damage, the location, we didn't have any exact idea of these values at the time. So these damages that we put on this structure are ideal representation of the actual quantities that may be found in practice. So under the same loading and boundary condition, we analyze all of these damage integrated models, and we monitor the same type of response, load versus deflection at midspan of the structure, and we compare this response to the intact system. So as you can see, in all cases of damage, we have reduction in the overall capacity of the system as a result of the integrated damage mechanism. And other than that, if you compare this reduced capacity with the nominal design capacity, you see that we also have reduction over the reserve capacity of the system. In some of the cases, we also have reduction on the ductility of the bridge superstructure, which can be defined as the ratio between the maximum deflection that the bridge can reach, or the level of deflection that the bridge experiences at the moment of first yield in the girders. Among all of these damage cases that we consider in this study, as you can see in this table, girder corrosion. With the girder corrosion, we have the most severe effect on the system ductility, almost 76%, and with the fire attack, we had the most severe effect on the capacity of the overall capacity of the system, which is almost 53%. So with that sensitivity study, we wanted actually to expound our investigation to evaluate the behavior of actual in-service structures, and we selected Virginia as our testing bed. According to NBI national report in the 2013, almost 50% of bridges in service within the state are string or multi-gilder bridges, and within that classification of bridges, almost 32% of those are classified as deficient. So actually, this was the motivation for us to see how these in-service structures within the state might be performing under the effect of existing deterioration. So So in order to that, we decided to perform a parametric study on a couple of representative structures within the state. But the problem that we had actually two challenges at the time. The first one is how to select these representative structures. So we had the access to the inventory database of the Virginia Department of Transportation, and we selected two cases, as you can see in these pictures. The Eyelet Bridge and the Creek Bridge, and these structures are selected as they represent the common geometrical features of in-service structures within the state. And both cases, as you can see, these are multi-span, simply supported structures. Regarding the cross-section, both of them, they are composite steel girder bridges with built-up girders or roll-shaped girders supporting a uniform thickness reinforced concrete slab. And we evaluate one slab for each of these structures. The other issue that we had at the time was to have the knowledge regarding the range of damage conditions that may occur in the state. So although we had the inspection reports for both of these structures, but these are our representative cases. So we want to know how the existing range of damage within the state might affect these representative structures. So at the same time, we prepared this questionnaire or the survey and passed it along to the VDOT engineers and inspectors in 9 different districts within the state and asked them to provide the average range of damage that they observe within the state. As we received their responses, we realized that most common type of damage that they observe in the state are corrosion in the girders and deterioration in the deck. So with that, we moved along with the parametric study when it started to investigate the impact of corrosion in steel girders on these specific structures. So for both of these structures, we created numerical models in the same approach, in the same methodology that we used and validated in phase 2 of this project on both of these Eyelet and Creek Bridge. In order to integrate the effect of damage, we refined the mesh generation at the either end of the structure, and this mesh refinement actually allowed us to model the exact detail or geometrical detail of the damage area. And the damage modeling was in the format of reduction in the thickness of the elements because of the existence of this corrosion. In reality, in real practices, corrosion between different girders might be different because of the environmental condition or the level of the attack of the corrosion. But in this case, we assume to have a uniform and identical stage of damage for all of the girders at either end of these simulated bridge superstructures. Regarding the damage scenarios, as I mentioned before, we prepared this questionnaire and we asked the engineers to provide us the minimum, maximum, and average level of observed deterioration within the state. So as we got the responses from this questionnaire, we ended up having these 9 representative cases, and we tried to include the variations over shape, depth, and extent level. So as you can see in this figure, the first 3 cases representing the damage scenario that we have the rectangular shape or the corroded area. On the second 3 cases, we have triangular shape, and the last 3 cases, we have trapezoidal shape. As we go from the left to right side, we have more expanded area of the damage because these dimensions of the damage are related to the dimension of the member. And also, again, from left to right, we have more depth of the damage, from 5% reduction in the thickness to 20% to 50%. Regarding the analysis, we performed the same type of analysis regarding boundary condition. We applied simple supported boundary condition for both of these structures as they're reported in their as-built plans and also design plans. Regarding the loading configuration, we consider to have flexural loading and shield loading scenario where we put the truck loading at the middle span of the structure and also close to the supports. Regarding the material nonlinearities, we included all sorts of material nonlinearities in the models, and all the assumptions regarding the modeling of the details of these structures are very similar to the one that we validated in phase 2 of this investigation. And then in this specific case, as we have degraded girders, there would be a potential for lateral buckling and local instability for the girders. So we also included the geometric nonlinearities into our model. So we ended up having 40 cases of analysis for both of these structures. And the main goal of this phase or this parametric study was to understand how these assumed type of damage will affect the safety of the system. So if you recall from phase 2 of this investigation, we argued that in this type of structures, girder type bridge superstructures, we have a significant amount of reserve capacity. which is attributed to the fact that we have the high level of redundancy in the system, and that additional reserve capacity actually gives us a margin of safety. So we can argue now that the level of the safety in a bridge superstructure has a direct correlation with the system redundancy. And according to the literature, we have several definitions for the redundancy, and the most famous one is the redundancy is the capability of the system to sustain traffic loads after damage occurred to one of its members. But most of these definitions, they are qualitative, and in our study we needed to come up with a quantitative measure of redundancy to see actually how this damage condition may affect the safety of the system. So in order to do that, we actually implemented the analytical approach that was first proposed by Golson et al. In NCHRP report. They call this approach a direct analysis approach to define the value of redundancy in the structures. And they argued that the structure can be considered as safe if it is safe against the first member failure, the structure does not yield its ultimate capacity under the traffic loading, does not produce large deformations, and finally should be able to carry some traffic loads after damage occurred to one of its members. So these are, these are the limited states, and for each of these limited states they defined this, some target values, and they defined those target values based on the reliability analysis that they perform on a series of hundreds of structures in service and are believed to be redundant structures. So comparing these, the loads according to each of these limited states that we define from the numerical analysis to those target values, we'll have the reserve ratios, redundancy ratios, and comparing these redundancy ratios with the reserve ratio of each of these members, each of the members of the structure, we'll have the redundancy factor of the system, which gives us the idea of the level of the safety of the structure under the effect of any type of simulated damage. So we performed the analysis and followed the same procedure that they proposed for defining the values of redundancy factors. And these are the representative results that we had for one of the structures for both flexural and shear loading scenario. Between all of these numbers, I would like to have your attention on the boxes for the shear loading scenario. So each of these boxes, we have 3 boxes. The first 3 cases, or the first box, actually refers to these 3 cases are referring to the case that we have rectangular shape of damage. The second 3 cases referring to the case that we have triangular shape for the damage, and the last 3 cases trapezoidal cases. So as you can see, for each of these categories, as we go from case 1 to 3, case 5 to 6, and 7 to 9, we have more reduction in the capacity of the system as we increase in the intensity of the damage. But if you compare these boxes together, you can see that the shape of the damage does not have major impact on the values that we have. So we can argue here that the shape of the damage or corrosion does not have major impact on the capacity of the system, but it is the extent level and reduction in the thickness that may dictate the behavior and capacity of these type of in-service structures. We performed the same type of analysis for other structures, Greek bridge, and we realized that in addition to the loading scenario and also the damage cases, the geometry of the structure itself may have significant impact on the level of safety that a structure can provide under the different simulated type of damage conditions. And at the end, we defined the redundancy factor for the system for both of these systems for shear loading and flexural loading scenarios. And as you can see in this table, all of these values are larger than 1. So it means that these selected structures under the selected range of damage, they are safe to operate. But if in any case you receive the values of which is lower than 1, we need to stop the operation of that specific structure. We need to perform appropriate maintenance program and check these redundancy factors again to see if we get the value higher than 1, and that time the structure is ready to get back to service. This is actually the core of investigation that we performed to understand the effect of corrosion steel girders on the serviceability and safety of in-service structures. The second part of this parametric study, we try to understand the effect of corrosion in rebars and subsequent delamination in reinforced concrete slab on the behavior of these type of structures. So as opposed to the previous case that we include the existence of damage in a pretty much simple way by refining the mesh and reducing the thickness. Modeling the effect of corrosion in the rebars and consequential effects such as delamination is pretty much complicated. So mainly because of the details associated with these damage mechanisms, and sometimes we need to have modifications, very detailed modification over the material and geometrical properties within the damage area. So in nature, generally, delamination can occur at any location over the surface of the slab. It is not like the corrosion in the girders that may occur at the mid-span or specifically at the end of the span of the bridge superstructure, and usually being detected in the inspection programs as the percentage of the total area of the deck surface. Within the corrosion, reinforcement can experience corrosion from one side, and the corrosion can propagate all the way around to the other side of the reinforcement. So the fracture plane that can happen within the deck can occur at the upper surface, lower surface, or both surfaces of these corroded rebars. So this is the other detail that we need to include in our model. Delamination can occur as a result of corrosion in the upper layer of reinforcement or lower layer of reinforcement. Other than that, the other geometrical feature that we need to play around with is the reduction in the cross-sectional properties of the corroded rebars. So in the case of uniform corrosion, we may not need to address the material properties, but in the case of severe corrosion where we have effects of pitting, we also need to modify the material properties because we have degradation over the material properties of the reinforcement. As a result of expansion of these corrosion products around the rebars, we have internal pressure acting on the surrounding concrete. And as a result, we may have macro cracks, especially in the concrete cover area. So this is the other detail that we need to include in the models by reducing the material properties of the concrete in the delaminated area. And the last feature is the bond behavior between the reinforcement and the surrounding concrete, which can vary from the perfect bond to the ideal debonding, which this ideal debonding would be the lower case or the lower bound of the behavior of the system under the effect of delamination. So in order to understand the behavior of the system under the effect of delamination and corrosion of the rebars, we updated one of the bridge models that we had, the eyelet bridge, with 6 representative cases that, again, we selected them based on the responses we got back from the VDOT engineers. And as you can see in these figures, we selected 3 levels of propagation from 5% to 10% to 15%. And for each of these levels of propagation, we selected to have 2 different patterns, the concentrated pattern and the scattered pattern. And within these 2 patterns, we actually included the random nature of delamination into our analysis. Regarding the modeling, we assume to have delamination occur as a result of uniform corrosion in the top layer of reinforcement. So as a result, we didn't consider any degradation in the steel material. We assume to have 30% reduction in the concrete cover at the location of delamination, uniform crack width of less than 1 millimeter. We assume to have the upper surface fracture plane for all of these cases, and finally the ideal case of debonding in all of the simulated models. In the analysis regarding the boundary conditions, we assume to have the same simply supported boundary conditions according to the as-built plan and design plans. For the loading scenario, we only include the flexural loading, mainly because of the location of these delaminated regions. The flexural loading will cause the worst case scenario with respect to the ultimate effect on the ultimate capacity and also ductility of the system. So we apply the load, it performs same type of analysis, and we monitor load versus deflection at midspan of the structure and compare the result for all of these 6 damage models to the intact model, which you can see in the blue lines in the following graph. What you can see is that generally delamination does not have major impact on the overall behavior of the system. It doesn't have major impact on the evolution of material nonlinearity, including the cracking in the reinforced concrete deck and yielding in steel girders. Other than that, you can see for all cases, we were almost able to capture the same level of ultimate capacity for the system. So there's no major change on the reserve capacity of this system over the design or the nominal design capacity. So with no change on the reserve capacity, it means that delamination does not have major impact on the redundancy, and as a result, we can say the lamination itself does not have a major impact on the level of safety of the structure. But as you take a look at this figure, all of these red dashed lines, we have the reduced ductility in the system, and this reduced ductility is mainly attributed to the fact that because of delamination, we lost composite action between the layers of the concrete. And this loss of composite action helped the compressive stresses to increase significantly at the top surface of the concrete and cause premature crushing, specifically at the margins of the delaminated areas. Other than that, if you take a look at the results that we tabulated in this table, within each area of the damage, for the scatter pattern, we have more severe effect or more severe degradation on the capacity of the system. So this is pretty much the parametric study that we performed on these representative structures, and that was the last part of this ongoing investigation. In summary, the overall objective of this research project was to establish a framework to evaluate the behavior of in-service structures under the effect of different types of deterioration. This investigation that we performed so far is limited to composite steel girder bridges, as they are believed to be one of the most common type of structures in service, and we studied the influence of corrosion steel girders and delamination in the reinforced concrete decks, but the idea and the framework is generic and can be applied to any other type of structures. Upon analysis and parametric study, specifically in the last part of this investigation, we realized that corrosion has major impact on the behavior of the system, and the level of this effectiveness of this impact highly depends on the damage extent level. Delamination has minor impact on the nonlinear behavior, while it may reduce the functionality of the system because of local crushing failures. The proposed framework could be beneficial for preservation community, as it can support them within their decision-making processes, and also can provide the linkage between design and preservation communities, which are not really connected in nowadays practices. So before we go and talk about the future potential research, I would like to ask you guys about this question. What do you see this study being useful? A, application of load rating of existing structure. B, load testing programs for research purposes. C, maintenance and preservation decision making. And the other ideas, if you have, we would be happy to have your ideas on the other potential application of this framework. You're more than welcome to fill in your answer in the chat box or correspond with us through email addresses. All right, thank you very much. I appreciate it. And the last topic I want to talk about is the potential future research as a result of this investigation. So this study that we have done so far is limited to just two types of damage, corrosion and delamination. We may also be able to study the effect of other damage scenarios such as vehicle impact, vehicle collision, or fire attack. We studied the effect of these damage conditions individually, so we can also expand the investigation to study how these couple effects of these damage cases will influence the behavior of the system. Our investigation, again, was limited to composite steel structures. We can expand the investigation to other type of structures and also corresponding type of damage with those new structures. We can also expand our numerical models by including the substructure and foundation into models, which actually allowed us to include the other damage cases such as scour, flooding, and also other loading scenarios such as seismic loading or vehicle bridge interaction or water-soil structure interaction. I want to give you guys a heads up on the upcoming presentation. We're going to be presenting some parts of this investigation in the next year TRB annual meeting in the session 499 on special topics in steel bridges, and also in the next year Structure Congress in April in Portland, Oregon. and will be on the session 2005 on the bridge assessment and health monitoring. Well, thank you very much for your attention. This is the list of papers that we have published and presented in several conferences and journals. Most of them have been established, and we have still a couple more papers that are still under the review process, and we look forward to having the reviews back by the end of this year. Thank you, and we'll be happy to answer your questions.
Yeah, so I think that was really great. I really appreciate Dr. Harris and Dr. Gatazi doing our presentation here. If you have questions, you can, I guess we can speak up. I don't think there's too many of us, but you can also type in questions in the chat box. You can, get to us in different ways. We really appreciate everybody's participation today, and I think we did have a lot of participation with the polls and everything. So that sounds great. So I guess my question beyond, so the colored bridge elements here, that's just a pretty bridge, or does that have to do with?
It's just a representation.
It's just a representation. Okay. So I guess my big question is, you said that one future research thing is to combine the two degradations. Is that where you're heading next, or what specifically are you doing next?
Well, what we've actually done is, I would say we put steel girder bridges on hold for the time being. It's the topic of Amir's research. And we have a parallel project that's going on looking at pre-stress girders where the mechanisms are going to be a little bit different, where we have things like corrosion of the internal reinforcement, potentially leading to brittle failures. So the deck stuff will be the same. The corrosion mechanism in the girder will be a little bit different. So that's actually the next phase of this particular project.
And so anything girder is steel, or not necessarily?
Any girder representing the primary superstructure member, primary load resisting member in the bridge. So the deck is kind of the the riding surface and the transfer of load from the vehicle down to the primary load members. So the deck itself, it's pretty universal, right? Steel girders, pre-stress girders, reinforced concrete girders, same type of deck. And then the girders are what changes.
The material is different.
And the design. The material and design, the failure mechanisms are different.
And damage mechanisms.
And the damage mechanisms will be different as well.
But by understanding the damage mechanism for the girders here, is there correlations with how damages happened on other bridges, other materials?
Well, I would say that it would correlate with other types of steel structures, but these are beam bridges, so it's a beam with a concrete deck typically. So there's other types of beam bridges. So there'd be something like a box beam where they're spread or side by side. We have pre-stress I-beams, bulb tees, other type timber decks, steel girders. So there's a whole variety of beam type structures that are out there, and their deteriorations are going to be slightly different as you go from one to the next.
Cool. So I guess I don't want to take up or manipulate the conversation here. If there's other people who have questions, for our two presenters, we haven't lost everybody, so I don't know whether they are, or if you guys are waiting to have questions or curious about the discussion, or...
You see, this is it. Why does that show up on mine?
Oh, maybe you guys have questions and somehow I'm not, or maybe they wrote just to you.
Oh, okay.
Okay. We're kind of, okay. So we did get somebody to say hi, and hopefully they have a question here. Or maybe a few people have questions. So, yeah, definitely please respond. I don't know if you guys are muted, so I mean, I think you may be able to speak up. But here we go. Use of geometric optimization in bridge design. One of you guys speak to that?
How to use it. It's actually, it's a sort of a topic that we're starting to explore. It's actually not part of this particular study, but as it relates to this study, one of the areas that we could start exploring would be, can we optimize preservation decisions? Things like, do we need to overlay structures after they've been milled down, or things like that. So I think you could have some relevance there. I think it would be difficult for me to explain how to use the optimization tools. There's within ANSYS, for instance, there are some optimization tools that exist. You could optimize the shape and geometry of the structure, minimizing things like material, balancing stresses. So I guess if you have questions or comments on that, it's probably better to answer those offline than here.
Okay, and we did get a good presentation, thanks, so that's exciting. So I guess Ashke likes the input. Professor Harris, that's great. We got Jimmy asking a question. Yeah, John, can you check it from KPI? Those were oh, we have no questions, thanks. And I think somebody else was typing. But again, if you want a professional development hour, or like a certificate recording that you attended, please send it in. And I guess Ashke has another question about whether we work with transportation engineers on vehicle-bridge interaction.
To be honest, we haven't. The vehicle-bridge interaction is something that Amir and I have explored previously. It hasn't gone very far. We sort of started with this concept of basically using bridge vehicle interaction for structural health monitoring, so basically input-output type response. And we kind of went down this path for a bit, and then we really want to understand actually just the system behavior of the structure. So we have started down this, but we haven't really fully developed that idea.
Here's a quick question. Evaluating the possibility of increasing the air content on the concrete to compensate for the expansion of the reinforced steel when corrosion takes place. That definitely sounds.
Yeah, it's an interesting concept. We haven't really. It's, I would say, more on the material side, and that's more on the design side than anything else. It could be. I'm kind of speaking off the cuff here, but it could be something that could be explored with respect to maintenance and preservation decisions. When you have existing rebar that's corroding and the expansion occurs, maybe the overlay can accommodate the expansion. But I think that's a very interesting point.
Okay, cool. So yeah, we may have lost our network connectivity, so if you're asked another question, we might not be getting it.
I'm still online.
So we're still online. Okay, so again, if you're looking for a certificate of attendance, please email Jennifer Butler at jab8md@virginia.edu. And I do appreciate everybody's attendance at the webinar today. Hopefully your connection's working better than mine. We got another question. Yay. Okay. So go ahead. Or I guess. So they were talking about adding the air to avoid cracks in the thing, right? Right. And then.
Yeah, that was more of a comment than it was related to the first question.
Okay. And then I guess we'll type in the email for certificates.
Repeat Mrs. Butler's
email. So JAB8MD. Or PDH. Oh, okay, now I just got rehooked, so that's so weird. I don't know. So yeah, so thank you to Devin for just typing in about the certificates. We also wrote it in. So if you guys don't have further questions, I do really appreciate the attention and time that our presenters put into putting this together, and I really appreciate everybody joining us today and learning with us. So I'm hoping